Well, it's a great pleasure to have Raman Sundrum, an old friend of mine and a great physicist, worked on topics all over particle physics. And he's now going to tell us about cosmology and unification.
Great. Thank you. This is work done with my students, although Shobik, with whom most of the work was done, is now a postdoc at Berkeley. And there are the papers, and they're all in JHEP somewhere. As you'll see, as we keep going along, we're used to saying that, particle physics, the LHC, and so on, it's all pretty extreme already, in that you're doing things that are sort of almost impossible. And of course, in modern cosmology, you're also doing things that are almost impossible. I'm saying that even by the standards of that, we are going to be pushing things and looking at the intersection of extreme cosmology, extreme cosmological measurements and theoretical understanding, and trying to extract from it, I think, even by LHC standards, extreme particle physics. Okay. And the general subject, which you may have heard of, is called cosmological collider physics, where the universe is kind of acting as our collider in a precise sense. So, quick outline is going to be that I'll tell you about how very heavy particles with masses of order the inflationary Hubble scale can be imprinted on the fossil evidence in the form of primordial three-point functions, or primordial non-Gaussianities, as they're called, in the CMB large-scale structure or 21 centimeter high redshift cosmology. And then the question is, what is worth hunting? You got this incredible thing that can see incredibly heavy particles. In principle, what would you look for? And kind of maybe an obvious thing to say is, can you see grand unification explicitly? So I'll talk about that a little bit. Then I'll discuss this quick mechanism called heavy lifting that we found, where basically even the standard model, which we think occupies much lower energy scales than the inflationary scales, might somehow show up back in that inflationary era at comparable energies to the Hubble scale of inflation, basically due to the hierarchy problem. So here the hierarchy problem could actually be an advantage. And then the final two topics are basically in pursuit of stronger signals, because these are incredibly weak signals, and bigger windows of opportunity, okay, a wider range of masses that you could see. So the basic idea comes by looking at how inflation solves one of its main targets is solving the horizon problem. And so here is the pic. Let me see if I can get my pointer out here. So the vertical direction are sort of co-moving length scales. So the redshift is factored out, and those length scales stay constant in co-moving units, and then time is on the x-axis. And if we just started from the Big Bang, then there are length scales that would have actually been outside the co-moving horizon. They would have been outside there are length scales that are outside causal contact during the time the CMB was laid down, but which we are now able to see. They've come back inside the horizon and we're able to see them. And of course, what we see famously is that the CMB looks quite equilibrated, which is usually a sign that those length scales should have been in contact with each other. And they couldn't have had time to do that if we start time off at the CMB, at the Big Bang. So inflation posits a earlier era where the expanding in such a way, accelerating in such a way in its expansion that the co-moving horizon is actually contracting. And then these length scales could actually, if you go far back enough in time, have been in causal contact to have equilibrated or contacted each other, helping us to understand why the CMB looks the way it does. Okay, so that's a quick cartoon thing. I don't want to spend more time on that, but it is the backdrop to the story that I am trying to tell you. which is really a story of seeing incredibly massive particles wandering the ancient landscape during inflation, and you really want to see them. You want to see the movie. Now, the plan is based on the way that you solve the horizon problem. So if there are these ancient ancestors of particle physics wandering around at these very early times, then what you'd like to do is that as they exit the horizon, they freeze, like a, the perfect caveman or something freezes, and then survive for long periods of time until they re-enter the horizon, which starts thawing them. And then hopefully before they decay too much, we see what's going on, and we see, there it is. It's incredible. We see the caveman of particle physics wandering around, or the dinosaurs of particle physics wandering around. So that's the idea. Of course, there's the, it's not literally that you're going to bring back those actual dinosaurs. What you're really looking for is to bring back the home movies of those dinosaurs. Okay, so you really want to say, I'm actually going to see the propagation of these heavy particles, literally propagating, but they're not actually being brought back to life. I'm just seeing some record of them. I'm seeing the movie of them brought back to life, because these ancient particles, in order to have an efficient way of recording them, have to decay into inflatons. Okay, but then the story is that we need to freeze that data and then bringing it out of cold storage now there's again a kind of a puzzle, which is just the obvious one. What ancestors of particle physics would have been around during inflation, where inflation is constantly inflating away everything and emptying out the universe? Who would be around? But that worry neglects quantum mechanics, where basically we have the E equals mc squared to create particles can be provided by the curvature of space-time, or if you want, the acceleration of the universe, the Hubble scale during inflation. So I'll usually use h, or I might use 1 to represent the Hubble scale of inflation, but it could be as big as, really big scales, 10 orders of magnitude above the LHC or something. And in that case, you might think that you could create particles which are 10 orders of magnitude out of range of the LHC, and it would be great if we could somehow then see them, okay? So to just set some of the classic things that you know of, but I'm trying to get you to look at them in a new light. Here's slow roll inflation, and the kink in the picture that I showed you with the co-moving length scales is caused by inflation, where classic picture, a scalar field is very slowly rolling down this hill, during which the energy density of the universe is approximately constant, and the gravitational solution to that is an accelerating universe or an inflating universe. And then eventually, however, that ends, and somehow the energy in the inflaton field is transmitted to the standard model in dark matter, and that kicks off the Big Bang in the traditional sense. And during that, what's key is that there are quantum fluctuations that modify, that kick around the classical slow roll evolution, so that it either it's retarded or advanced at different places in space relative to the overall classical movement. You've got small retardation or advanced effects of order Hubble, which then turn out to adjust when exactly reheating takes place. It'll here or there, reheating will take place at different times because of these quantum fluctuations, and we can work out based on that what this sort of how the fluctuations in the field phi turn into fluctuations in the reheating time. We can sort of get it from here, that the translation between the retardation in reheat times versus field space is given, of course, by the field velocity. And to fit the data in the CMB, that says that the field velocity is actually large compared to the Hubble scale. Okay, so that's something to just remember for later, that the field velocity is large. But while you're up here, approximately at the level that we're going to need it, because we're going to be working out small effects, and we don't need to multiply those small effects by another small effect, which is the fact that this slow roll is not perfectly standing. The ball is not standing, it's slowly rolling. Still gives us approximately de Sitter space as the solution, as if it was just a cosmological constant. So for a long period of time, the universe has an approximate solution given by de Sitter space, which I've written in these so-called conformal coordinates, where it looks like a Minkowski metric in terms of a fake time called conformal time, divided by conformal time squared. Okay. Now, I've already written in h equals 1 units, so I will often slip into h equals 1 units when it's painful to keep h around. But whenever you see an h or a 1, that means or the dimensions don't match. It means that I'm in inflationary Hubble units. And the spatial coordinate is the co-moving length scale, so the conjugate momentum is conserved, but of course it's constantly getting redshifted by the redshift factor 1 over eta, which is the 1 over the conformal time. The real time dt is related to d eta over eta, so of course t is really log of eta. And you can try to understand, therefore, what happened to time translation invariance. Well, you've got a time-dependent metric, so time translation invariance doesn't hold in the usual sense, but it does hold almost hold in the sense that time translation invariance would be t goes to t plus a constant. Since eta is really the exponential of proper time, that's the same as eta goes to an exponential of that constant times eta. But that's not a symmetry unless you accompany it by rescaling space. Okay, so you can say what kind of pattern these quantum fluctuations are going to imprint on data that we can see by saying what's going to happen by the end of inflation, where you match on to the hot Big Bang. The end of inflation is late times, and in these coordinates, late times is actually eta going towards 0. And you can see that what happens to this time translation invariance augmented by scaling as eta goes to 0 is that eta stays fixed. Eta equals 0 is fixed by it, and all that's left is this spatial rescaling. So spatial scale invariance is the famous feature of inflationary perturbations that follows from these symmetries of de Sitter space. Okay, so these are the two things to keep our eye on. So the other thing to keep our eye on is that the pattern that is laid down from all these inflationary perturbations due to quantum mechanics during inflation, if you sort of took the picture at reheating, the time that inflation ends, it's really creating, as you'll see, I mean, I'm saying this, but that's because later the formulas will look like this, that it creates a kind of course, the reheating time, the instant of reheating or the era of reheating is really a three-dimensional surface in space. And it's a kind of a hologram for time, okay? In the sense that if quantum perturbations create, so here I am being created in this picture, that's me as a baby. But if I'm created early on, then by the time that image gets to the it's created later and it redshifts to time eta equals 0, but it redshifts less, it looks smaller. And here I am right now, but that means that it's even later and there's less redshifting, and so it looks smaller. So there's a kind of relationship between the pictures in terms of size versus what their timing is. The thing is that if creative processes, if everything we're going to see is something that has to be created by quantum fluctuations, then this creation of me could have happened at any time, in which case the picture looks more like this, okay? That there are little me's being created and then evolving and growing older in all sorts of ways and all sorts of places, this is getting laid down. And so ultimately, when you look at the picture of this time hologram, which, for example, is the CMB, right? That's an example of a picture of that type. It, A, will have a kind of fractal look to it, and B, it'll be so crowded that you're going to have to figure out how to decode it. So it's exciting in a way for theorists that the kind of methodology for decoding all of this happens to be very similar to the methods of three-dimensional conformal field theory. Maybe as sort of elevated into a conjecture in the form of the DS-CFT correspondence, but this fact is already older than that correspondence, okay? So keep your eye out for this aspect. Okay, so let's just do the simplest thing, which is massive particles in de Sitter space. And these massive particles, which I'm calling chi, let's just think of them as the target ancestor particle. Okay, this is not a super exciting particle, it's just a scalar, but let's just see what it does, okay? So it's not the inflaton, it's some other massive field. So there is its usual space-time incarnation. But now I'm going to just Fourier transform space, but not time, to take advantage of translation invariance, at least in space. And I get something with a lot of redshift factors thrown around. And if you look at the equations of motion for this free field, then they are of Bessel type. And in particular, the solution, again, for this kth momentum mode, co-moving mode, so this is the conserved momentum, has this normalized form in terms of Hankel functions. It's the particular linear combination of Bessel type functions which has the right behavior as we go into the early past, where we can make contact with our Minkowski instincts. So let's just see why. So first of all, I'm going to take M to be larger than Hubble purely to simplify the formulas, not because it's absolutely essential, but when I show you final results, I won't use that approximation, but it'll just be easier to get the idea by doing that. So instead of a Hankel function, you just, you have a little bit easier in terms of this index, just looking like this. And now if I go one more step and go to very early times where eta is, so where k eta, early relative to 1 over k, when k eta is much bigger than m, so early times is large negative eta, okay? So when k eta is much bigger than m, then you can approximate this Hankel function in this way. And remember, when you're going to very early times, whatever the wavelength k is, it gets, the physical thing gets blue shifted in because of the expanding universe run in reverse, it gets blue shifted so that it's much smaller than the Hubble scale or the Hubble length scale. So it effectively thinks of itself in flat space, and you get this very familiar flat space behavior for an ultra relativistic short wavelength particle. It looks like a plane wave in the usual normalized, relativistically normalized sense. Okay, so that's what chose the normalizations. But on the other hand, if you go to late times, again, just in the other regime, you find that you get these two terms. Now this term, in my usual metric of plus, minus, 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 this usual thing is nothing but the standard propagation in physical time, where it's say log eta. It's the usual positive energy E equals mc squared, and its energy is totally given by the mass because it is redshifted away all of its momentum. All of its spatial momentum has been redshifted away, and so the mass is all that's left. At early times, it's blue shifted so that the momentum is more important than mass. But there is this other term, which has negative energy. If this is positive energy, this is the negative energy guy. And so the question is, what's going on? Negative energies, what a disaster. Now, we've already litigated this question of negative energies in field theory and flat space in the first half of the 20th century. And so the answer is obviously that it is secretly telling you this is just a bad first quantized theory, where if we had only gone to a second quantized description, it would just be saying that there's an amplitude to create pairs of particles. at roughly the crossover between these two regimes around this time, okay? And this factor here is nothing but the amplitude for that pair creation. And it's usually, for large M, we usually say it's Boltzmann suppressed, because the probability for creation is the square of this, e to the minus 2 pi m, and you can think of that as basically a Boltzmann probability in a thermal equilibrium if you identify the temperature as the Hawking temperature of de Sitter spacetime. Okay, so that's sort of the quick connection as to how you should have thought of it as something reasonable before you worked out all the math. That's it. Okay. So I won't go in this talk into all of the second quantized formalism because that'll take too long, but this is the engine under the hood that's doing it, okay? So the other thing you need to know about is primordial non-Gaussianities from in correlators, which is the formal statistical tool that we're supposed to use to see the propagating particles ultimately. But the first thing is just to understand the general structure of it. And it's given by saying, again, this is time going in this direction from negative eta to eta approximately 0, where we suddenly switch over to the Big Bang, inflation ends. And we're looking at 3-point correlators for reasons that you're going to understand in a minute, why we do it, where we're looking for fluctuations, quantum fluctuations in the inflaton at 3 different points. And they have a 3-point function because presumably they're interacting. At some level, they're interacting, okay? And because quantum kicks to the inflaton show up as quantum kicks to the time at which you reheat, which then show up as quantum kicks to the temperature of, say, the CMB as a function of space, that means that these sort of perturbations in the CMB temperature or density in large scale structure is proportional to basically the 3-point function of the quantum 3-point function of the inflaton perturbations. So this is the classic kind of field theoretic observable, so-called in formalism, in the sense that this factor with the I epsilon is basically chosen to take the Fock vacuum, the non-interacting vacuum, and project it onto the interacting vacuum, just like we do in flat space, for sufficiently small wavelengths. Remember, it's only at sufficiently small wavelengths that you expect to be in an empty vacuum, but as the universe redshifts and the wavelength grows, then we actually do have particle production, as I just showed you. So this thing projects in the right way onto an empty vacuum, an empty ground state, when you go into the far past where every mode is blue shifted to be very small in wavelength compared to the horizon scale.
I have a question.
Yeah.
First question is why quantum fluctuation is determined by the Hubble expansion parameter during inflation? That's my first question. My second question is the integral of time, why it goes to minus infinity, go to plus infinity. If I remember correctly, the eta is the exponential t. So if t go to plus infinity, does it mean eta go to plus infinity?
Sorry, I was maybe because you're in a big room, so I was getting a slightly garbled version. Can you say that slowly or with fewer words? I will attempt to answer.
Okay.
Or John, if you're closer, I don't know who's got the mic, but or the camera.
Yeah, the integration region for the t is minus infinity to the plus infinity.
Yes.
But if I remember correctly, you just told us that the eta is the exponential function of t, right?
Correct.
If t go to plus infinity, does it mean eta go to plus infinity?
No, eta is more like, eta is e to the minus t, okay? So as t goes to infinity, eta goes to 0.
Oh, it's minus. Oh, yeah, got it.
Yeah.
My second is
yeah.
why the quantum fluctuation is fully determined by the Hubble expansion parameter during inflation. For example, which means if no inflation, there's no quantum fluctuation. That's the interpretation.
No. Yeah. So there are actually quantum fluctuations. Even, in other words, there are virtual fluctuations even in Minkowski space, as you know. If you, and especially there would be something vaguely akin to this in flat space if you were to work out correlators, not like in the S matrix, but you were to work out correlators of field theory at some finite time, say t equals 0, if you had some way of just doing experiments in that way, then there indeed would be quantum fluctuations of this sort. What's different, especially about de Sitter space or an expanding space-time, is that the fluctuations, having been created, they can grow. Another way to say it is, in standard Minkowski space, the fluctuations are describing the uncertainty principle, which says something like, intuitively and physically, I mean, the way an experimentalist sees the results is, it's like vacuum polarization. It's as if there are some particles there and they have energy, but only for a short period of time, because you always have to pay back the loan. It's only a loan from the uncertainty principle. Whereas what's happening in de Sitter is more like this idea of the Hawking temperature, right? That it is something that's actually able to create particles on shell. I mean, they're really there. Technically, it looks like you are, in a sense, just like in Minkowski space, it's a kind of quantum fluctuation in the same sense, but these fluctuations can actually exit the horizon and stay with us. So you get to keep what you fluctuated forever. And the energy, of course, the actual energy to do that is coming from the time-dependent background, which you don't have in Minkowski space.
Okay.
So that's my sort of intuitive version, and then we compute.
Okay.
Yeah. So necessarily these, this kind of thing is just summarized in this way. Of course, it's always got a delta function momentum space, just because spatial momentum is conserved at least. And this remnant is called the bispectrum, okay? And just done in position space. And notice all the time, oops, all the time has gone out of it. It's just a function of these momenta. And I see that there is something in the chat. Yeah, somebody is asking about my PowerPoint skills, Lloyd Knox. And yeah, I'm sure there is. And I recall that there was some way of sort of moving it off to the side, but I forgot since the last time I gave a talk. So I will, when I'm referring to that, I will probably do this and you'll be able to see. Sorry about that. Hopefully it won't happen. Hopefully critical formulas won't be at the, well, they often are. Sorry. Okay, so the sort of the standard thing that's referred to that you make out of the bispectrum that is usually the thing quoted is called the primordial non-Gaussianity F. It's a function of the three momenta coming in. There's a kind of convention late, the field velocity during inflation is sort of the conventional prefactor. And you're also normalizing it by the 2-point function, which roughly speaking is the power spectrum, the famous power spectrum that we see when we look at multipole expansions of the CMB. That's essentially what we're doing, where instead of L here, it's the 3-dimensional K. So this is sort of a very Gaussian kind of spectrum. This is the thing that we're really after, and this is the thing that's usually quoted, which the main thing is the bispectrum inside it. Because momentum is conserved, it's very nice. You can picture in momentum space, the correlator is a function of triangles, where you just need to remember the sides, because the orientation of the triangle doesn't matter. It's, after all, rotationally invariant physics. So it's just the triangle in any orientation. In fact, what's amazing is even the approximately, even the size of the triangle doesn't matter because we have scale invariance, right? The scale invariance that I showed you before. So this is a really weird function. It's a function of just the shapes of triangles. Cool. Often, because people don't want to quote the entire function, if they just want to give you the going rate for this function, they quote this perversely named FNL, which is just the same capital F at the equilateral triangle point. And just as a going rate, if you say, well, what do we already know from the Planck satellite and the best measurements of the CMB? Well, what we know is that the going rate for this non-Gaussianity is order 10. Now, if you remember that this prefactor is 10 to the fourth, the field velocity is 10 to the fourth to fit the CMB already. And all of these things in Hubble units, if they were all order 1, if basically the non-Gaussianity was order 1, the theory was non-linear at an order 1 level, then the non-Gaussianity would be 10 to the fourth, but in actual fact, it's highly Gaussian, right? That's why we often say that the primordial fluctuations are highly Gaussian, because they're much less than the going rate of 10 to the fourth for maximal non-Gaussianity. Okay, so then one last thing, just in terms of measuring this, is essentially my only experimental slide, which is we're calculating quantum expectations when we do in perturbation theory. We're calculating quantum expectations, but we only have one sky. And so you might say, what expectation? But the good news is that we do get to make multiple measurements. Given a triangle, we can rotate this triangle in different ways, and we can even rescale it to some extent. And so I won't go into the counting because I always forget unless I go back and work it out. But basically, the kind of error bar, statistical error bar, is given by 10 to the fourth, which is the going rate for non-Gaussianity, but with a 1 over root n, not too surprisingly, where n, the modes that you're counting is how many of these momentum modes fit in the universe, which has got its current size, okay? So that's what's worked out for different experimental regimes here, where this is redshift, or in terms of the scale factor written in this way, the redshift that we observe different data at, or if you want radial distance outward from us. So the CMB is measured at redshift of 1,000, and the Planck satellite basically has access to 10 to the 7 modes. And that's why we get this kind of precision on non-Gaussianity, meaning we haven't seen it, but there are bounds, which are order 10. From large scale structure measured at low redshift, you can get more modes partly because it's a more 3-dimensional map. It's spread out in the radial direction. It's not a delta function of the radial direction the way the CMB seems to be. And that's exciting because it'll improve our precision on these things. And sometime this decade, hopefully we'll have data that's dramatically new. And the ultimate sort of holy grail of this subject experimentally is 21 centimeter high redshift cosmology, where one can hope to see a much more 3-dimensional map with many, many more modes. And one can, in principle, access, very tiny FNLs. And this, in other words, a dramatic improvement beyond what we've already done, okay? Okay, so how does this thing work? We just need to calculate a 3-point correlator with Feynman diagrams in the in language. And first we need a Feynman vertex. And so here is a classic possibility that the scalar field that we're trying to see is coupled to the inflaton, because that's the ultimate thing that we are reading out. The inflaton is the clock that determines reheating at different places, which determines temperatures in different parts of the sky. So we want to decay into that, into fluctuations of phi. They're usually derivatively coupled to ensure the radiative stability of the very flat potential that we need in slow roll inflation. So you have some non-normalizable coupling like this, and you can use it to draw Feynman diagrams like this. Naively, you might think it should be 2 to 2 with the exchange of chi. but you can actually take one of the legs and let it just be the classical background. So all of this quantum stuff is taking place in a classical background with a slowly rolling classical inflaton. So you can always put a zero momentum leg there, just like a VEV. But we are going to need 3 for reasons that we'll see in a second. And the momenta are routed like this. So I'm calling the momentum through chi K3, and then necessarily through this leg, it's the same K3, since this is just a background VEV. As far as space is concerned, it's just time dependent. And then K1 and K2 are up here, okay? Now, we should ask, let's estimate this answer, okay? So here is the bispectrum. There is this leg that's dangling. It started life up here as a phi dot, okay? It's a time derivative, since it only depends on time. It's a time derivative of phi, and that's that. So that's what that is. Then there are 2 vertices, so that's 1 over lambda squared. So that's what that, hang on, let me try it. That's what that is. But now we need to start the story. We need to start the story with pair creation. Now, the amplitude for pair creation, I showed you on that slide with the Bessel functions. The amplitude for pair creation is this Boltzmann suppressed factor. And then if we create it, we would like to observe it. We really want to see the dinosaur walking. Now, for particles, walking is this, okay? It literally is, in terms of the physical time, just this, okay? So that's what we think the answer should be. The thing is, who determines T late and T early? Who's getting to decide that, okay? And we'd like to be able to actually play the movie. So we'd like to vary T late minus T early and actually watch things move. So the good news is we control it. We control it based on the Ks that we observe, like which correlator we decide to measure. And we can see that in this picture, that if you remember, again, my Bessel function slide, that the time of production is basically K eta of order M. So that's the eta early. It's the time at which you produce this mode. And there's no other scale showing up in this side of the diagram. So it's basically the same, roughly parametrically the same time that it decays in this way. Or if you want, converts. In the background of this, it converts into an inflaton. But if K1 and K2 are much bigger, if they're much bigger than K3, then this time here for the final decay can happen much later, okay? That's given by this time, just in the same way I said for the Bessel functions. But this can happen later than this if we just make K1 much bigger than K3, okay? And why is this the decay time, though? Why is that the decay time? Well, you can just sort of think of this chi. It's redshifted, it's lost most of its momentum, and it's going to decay, and it's basically at rest. And it decays with two essentially massless inflatons back to back. And the physical momentum of each of these guys is the co-moving momentum multiplied by this red shifting, and the same here and here. And so in order for this big massive particle to decay into K, you have to wait long enough. If K2 is large, if K1 and K2 are large, you have to wait long enough, that is, eta has to be small enough that M equals 2K1, equals K1 plus K2 physical, right? So you have to lower the price tag in order to decay by redshift. So that's why you're guaranteed that if you just make K1 and K2 big enough relative to K3, you're guaranteeing that between production and decay, there is a long time. So if we plug that in, if we just plug what I just said there in, remembering that T is really log K, T is really log K, then you plug that in and you get this, okay? Which means that as you observe as a function of these Ks, you can dial, and out of the chaotic mess of overlapping images and all of that, you can extract this kind of propagation of the heavy particle And using this exponent, you could even measure the mass of the particle. That's the kind of spectroscopy you can do. Notice for the people who are sort of CFT inclined, this is really a kind of imaginary critical exponent from the sort of in the statistical mechanics or CFT language. It's a kind of scaling dimension or a correction to a scaling dimension, but it's imaginary because this is not a unitary CFT in the usual sense. Time is not actually part of these three dimensions of space for which this applies. So there's a kind of, as I said, this is just one illustration of something that one sees again and again, that there's a kind of CFT-ishness to the correlators that one plays with. The fact that it's non-analytic in K3 in particular is actually the sign. So there are, of course, various types of backgrounds, and there are various types of contact interactions that inflatons might have with themselves, but they will not give this non-analytic dependence on the momenta. They will be analytic, very much like poles in an S matrix are easier to spot against a background of contact interactions, which are analytic in momenta. Okay. Okay, so let's just try to apply it to a good solid target like grand unification. So as you know, if we just plot as a function of energy scales, the log energy, and we plot the inverse couplings of the QCD electroweak, QCD, yeah, SU2 and hypercharged couplings, and we extrapolate with the standard model renormalization group, they amazingly seem to sort of come close together. They seem to be meeting, or they are teasing us with getting very close to meeting. And you can say, what's up with that? And of course, we know one answer, which is that could be a sign that the forces are actually merging into some sort of grand unified group like SO10 or SU5. It's a sign that these grand unified groups were really operating at these incredibly high energies up here, whereas, you know, roughly 10 to the 14 GeV or so with some spread. And that at that scale, they somehow got Higgs to the standard model and then followed standard model normalization group to diverge in the infrared, taking away obvious clues so that we had to work harder to spot them. Okay, so that's great. It's grand unification, super exciting. This is the non-supersymmetric grand unification. We can talk about anything else later. But then we could say, wow, that scale, 10 to the 13-ish, if we're lucky, maybe that's the scale of inflation. That's a plausible scale of inflation. We could maybe go up there and look and see who's around, right? Maybe these are the answer, the dinosaur particles we'd like to see. Now, of course, there are two questions that you may be familiar with. One, why is it not perfect? It's good, it's pretty good, but why is it not perfect? And another thing is, look, if there are really some of these extra gauge bosons here, like the X gauge boson of SU5, it would mediate proton decay in this sort of way. 3 quarks could annihilate to a lepton. And the bounds on that are incredibly stringent. They would say that the mass of these heavy gauge bosons has to be bigger than the scale that we're spotting here. Significant, even though this is not very precise, it looks almost a bit of a stretch to be up here, but naively, if you want this to be the scale of inflation, then this is already ruling it out. It's already saying proton decay bounds would kill it. But there's a well-known answer to this thing of having to avoid proton decay and also even understanding what kind of things can fix this imperfection. And they all happen in the most simple way that I know of in Orbifold guts, which is basically a higher dimensional grand unified theory, where the grand unified theory lives in 5 dimensions, where the 5th dimension is, say, an interval between 2 end of the world boundaries. And basically the boundary conditions are what break the gut down to 3, 2, 1. So the boundary conditions only respect SU3 cross SU2 cross U1, but in the bulk, you have the grand unified theory. And therefore, the wave functions of different modes of the different Kaluza Klein modes is different between the standard model ones with some boundary conditions that respect 3 to 1 and beyond the standard model ones, extra particles which have different boundary conditions. Okay, even though the particles in the bulk look like they're interchangeable, the boundary conditions are differentiating the standard model from the BSM. So they have different KK spectra. And here's the standard model, starts at roughly 0 on the scale of the compactification scale, which is the scale at which you start to notice that the theory is not grand unified. It's of order, that's what we would traditionally call the gut scale, or 10 to the 13 GeV. And then you get Kaluza Klein repetitions. But then the BSM physics shows up sort of out of phase in energy space or mass space. So it's a little off because of the boundary conditions in this way. And different, if you think of SU5, then the colored and non-colored particles that are related to each other by SU5 are like the quarks and the leptons that are unified in SU5. The quarks might be part of the standard model, but the leptons, which are part of the same multiplet, are actually over here with a big mass, a big chunky mass, which means that the proton is stable. These quarks might have Feynman rules, that link them to these leptons, but these leptons are kinematically too heavy for us to be able to decay a proton into. Proton is at GeV, this is at order 10 to the 13 GeV. And in that way, this sort of mismatch is what stabilizes the proton, okay? So it's an interesting theory, and it gives us some motivated targets for cosmological collider physics, like how about the fact that even the graviton has Kaluza Klein excitations, okay? That's a target for us. Or one of these, say, SO10 gauge bosons, like the Z prime of B minus L, okay? So we can try to look for these things. And indeed, this is one of the things that Shobik and I did. We started with the basic setup I told you, and then we put an inflaton and localized it to a 4-dimensional boundary of this 5-dimensional space, and then looked at what happened. Now, in the quick sketch version of it, which is not the final answer, but in the quick sketch version of it, it's very much like the scalar chi, where you put the Kaluza Klein graviton here, and it couples to everything, but in particular, it couples to the inflaton. And other than the indices, it looks very much like the scalar story I told you, with the scalar diagram replaced by this diagram. And so the answer looks very much like the scalar picture, except all of these indices have to tell you that there's some sort of angular, the spin is showing up in some way. The fact that it's spin 2 shows up in some way. And that's this factor here, this trigonometric factor here, where theta is the angle between the hard momentum and the soft momentum, okay? And if you work this out, if you just go ahead and plug in the numbers, you know the scale, right? It's 1 over m Planck. So go ahead and plug it in, then you will quickly find that you're getting an answer, which is interesting, but it's right on the edge of what we might be able to do with the kind of data that we are ever likely to have, where the non-Gaussianity is of order 10 to the minus 2. Remember the sort of numbers I gave you when I showed you the experimental slide. So that's one. But actually, just to say, so in order to work this out, one actually has to take into account that the inflaton energy back reacts on the extra dimension. And I won't go into this because I'm running out of time, but it's actually an interesting story of back reaction because it's right on the cusp of creating a kind of horizon, a black brane horizon that masks the other side of the extra dimension, which would, it's kind of a case, I'll say it in poetic terms, that horizon is really created by the Hawking temperature of inflation burning the other side of the extra dimension, and drastically changing the spectrum away from the thing we just made the estimate for. So anyway, there's some nice work of a number of people involving Nemanja, and we enjoyed working this out in more detail that I'm going to give you. But basically, we could work in a kind of approximation in which we can do the back-reacted problem between the stabilization of the size of the extra dimension in the presence of this inflationary deformation. And you can do it, and now here are the final, here's the results, where here's the mass of the Kaluza Klein scale, or the Kaluza Klein graviton, which is the Kaluza Klein scale, the compactification scale in Hubble units. And when they're comparable, but a little bit more than the Hubble scale, here is the going rate of the non-Gaussianity. And you see that if you are kind of in the magic zone, you can actually get bigger non-Gaussianities, so at least more obviously seeable. Not huge, but still much more of an optimistic thing to be able to see. And then you can work things out in more detail than my quick sketch, but I'm not going to spend time on that. When you come to the gauge part of the story, I told you about the gravity that's in there in the experiment. When you talk about gauge-Higgs theory in general, if you just talk about why not look for gauge theory? After all, that's the stuff the universe is made of. So let's just look for that. Well, the problem is that gauge theory has gauge charges, and charge conservation means that as long as the inflaton is something neutral, which appears to be in the simplest models, you will need loops of charged particles. So you have to actually create two pairs of particles and they annihilate this way, okay? Now loops are smaller than trees and they're harder to analyze than trees. So we noticed that, again, not rocket science, but if you are in the Higgs phase, then of course you effectively can just lose one of these lines into webs of whichever Higgs it happens to be. So that's the way to go. And even then, trying to find vertices that couple spin 1 particles, massive spin 1 gauge bosons, trying to find particle operators that couple them to the inflaton and give you vertices that you can see in cosmological collider physics is quite high dimension operators. You can sew them together by lower dimension operators and having some sort of mediator field. So that's totally fair game. But even then, if all of this is to be within effective field theory control, for reasons that I'll tell you in a succinct way later, you find that the signals that you get from spin 1 exchange like this are even more problematically small than the graviton exchange, the Kaluza Klein graviton exchange. They're down at the 10 to the minus 2 level if you're lucky, and then very rapidly Boltzmann suppressed if you go away from the perfect mass window. Okay.
That's the question?
Yeah.
Yeah, so either about this plot or the previous ones, for large mass, it seems sort of reasonable that there's some kind of decoupling going on. But can you explain what eventually happens at small mass? So in those plots it goes up and then your plot stops. What's actually going on?
Yes, that's a good point, and I can show you the answer right. Hang on, right there. So I'll say it in this way. Go back to this. So you can see it here. So I know that this was derived by assuming the mass was larger than Hubble, but trust me, something vaguely like the point I'm going to make is true regardless. So imagine this formula was just true. Then what happens when m, this is in Hubble units, h equals 1 units. So what happens when m becomes small compared to Hubble? Well, then this index goes approximately to 0. And so you lose this non-analytic sensitivity. So the answer to your question is you get some order 1 in the sense that this is not there, not a problem. So you get an analytic function of the momenta, and it turns out to be indistinguishable from a contact interaction of the inflaton, even though it's just a light particle that's being exchanged. So it's hard, there's an ambiguity in interpreting. So it would be there. It would be there as some kind of non-Gaussianity, but it would be there in a kind of analytic structure that makes it hard to interpret. That's the quick answer. That's why we like this kind of so-called squeeze limit, where we take this ratio and look for something parametrically non-analytic in it, right? If you were to plot this, and I'll show you a plot like this in a bit, you're really seeing something oscillatory as opposed to something where it's analytic, it's just powers. So that's the quick answer.
Can I just follow up just a little bit? So then on the plots,
Sure.
it seemed like you were stopping at M around, I don't know, 0.6, if I remember. I mean, it seems
Yeah.
like a pretty large number. Does that really where that washout happens? So you just stopped plotting where this effect gets large, or?
Yeah, no, that's right. So if I went back to, say there, right, then these things, these things they don't keep rising and rising and rising. What you're really seeing here is the onset of Boltzmann suppression. When the Boltzmann suppression is just 1, it just levels off.
Oh, okay.
But the rest of the functional form, so this is just the going rate when K1, K2, K3 are all equal. If you want to know how it depends, so here is the full answer, that even when, if the mass, let's see, so the mass is showing up in this parameter mu, and you can see what happens as M drops, this mu becomes imaginary, but that means I times mu just becomes real, okay? And you can see what the functional form is.
Okay, yeah, thanks.
So keeping in mind that at the moment, the problem is that the signals are barely on the edge of observability, which is exciting, but it would be nicer if they were even bigger. Let me say one more thing that is kind of magical, which is this heavy lifting mechanism, which is really dumb. Imagine that we were talking about the standard model Higgs, okay? So there's the standard model Higgs, there's its wine bottle potential, here's the tachyonic mass that is at the weak scale, of course, but you can always have couplings to the curvature, the Ritchie scalar, say, with some order 1 coefficient. You might think that's sort of the natural thing to have. Now, today, the Ritchie scalar is almost 0, so we don't need to take this into account when we're thinking about LHC physics. But during inflation, the curvature would have been the Hubble scale of inflation, which could be 10 to the 13 GeV, in which case this would be added to this as a kind of effective mass parameter for the Higgs. Depending on the sign, if it's one sign, it could just kill the tachyonic thing and restore electroweak symmetry during that time. But it can go the other way, and it can actually make the Higgs even more tachyonic. So electroweak symmetry breaking, instead of breaking at the weak scale, breaks at 10 to the 13 GeV. Okay, that's a robust possibility. Throw the coin and choose which one it is. But that means that the Higgs, instead of being very light, this is related to Marcus's question. If particles are very light, it's hard to see them distinctly in cosmological collider physics because you lose that non-analytic nature. That's true of our Higgs. But if this happens, if the heavy lifting happens, then our Higgs is transported into the golden window, roughly, of being of order Hubble scale, okay? And then we can hope to see it. So you might hope to see it, and of course, our Higgs getting a VEV of order the Hubble scale means that our Z gets a massive order the Hubble scale, the W's get massive order the Hubble scale, tops get massive Hubble scale. So in principle, all of these correlators can be examined and decoded for the spin and mass, just like we saw how spin is imprinted in the case of the KK graviton, the spin and mass. So you could do spectroscopy, and in principle, you could look at the mass ratios of these particles you're seeing in non-Gaussianities and say, my gosh, those remind me exactly of the heavier particles in the standard model. What a coincidence. Unless, of course, you take the obvious clue and say, those are the standard model, damn it. It's just, they've been shifted up in energies. Of course, they wouldn't be exactly that because there would be renormalization group effects that would modify them, but they would be renormalization group effects that you could hope to calculate, right? So this would be great, right? Except the signals are so, or maybe we could be seeing gauge theories in other sectors, other dark sectors. This would all be great, except the signals are so bloody small. What are we supposed to do? Hang on, I'm just checking a question in the chat. Ah, sorry, that's an old comment. So let me explain why the signals are so bloody small, okay? In single field inflation, I just told you that the field velocity is much bigger than the Hubble scale. It's an order 60 Hubble all squared. It's got units of mass squared. Now, whenever you have non-normalizable interactions, like we do here often, because we want derivative couplings to the inflaton to protect the potential from radiative corrections, then non-normalizable couplings will have energy scales in the denominator that are bigger than this scale, so that we have effective field theory control, okay? So that means that we're always dealing with couplings in these diagrams that have got this extra 1/60 to some power lurking, okay? Now this can be avoided in the non-minimal theory of inflation called the curvaton scenario, where the two jobs of the inflaton, one job of the inflaton, push the energy density of the universe to a approximately constant scale, V, which when multiplied by G Newton gives you the Hubble scale, okay? So this V is necessarily much bigger than the Hubble scale. So when multiplied by G Newton, I get the Hubble scale in Einstein's equation. That's one job of the inflaton. And the other job of the inflaton is to pick up quantum corrections of some sort, which depend on the nature of the slow roll potential, but to pick up quantum fluctuations which seed the inhomogeneities we see in the universe today. Those two functions can be separated so that the inflaton actually has very small quantum fluctuations by choice of its potential, and only is sort of driving the classical motion of the universe, in particular, classically giving you this big energy density that produces the Hubble scale, while some other light field, the curvaton, some other light field happens to have the larger quantum fluctuations, which is a function of its potential, larger quantum fluctuations, and the curvaton decays into the standard model and passes on its inhomogeneities to us. That scenario requires that the curvaton potential is actually subdominant to the inflaton potential, which is driving the Hubble rate. But in that case, the non-normalizable interactions to the curvaton are not bounded in this way. They can actually just be a few Hubble. Okay, so you can have stronger non-normalizable couplings. And then, just to give you some sporadic examples, even loop level diagrams or fermionic loop level diagrams can actually have these rather large non-Gaussianities, okay? Tree level diagrams can be incredibly large. All of that is possible. Even Z exchange can have FNLs, can have non-Gaussianities of order 1, which is definitely in the observable regime. So I've gone 5 minutes over time, so I'll just say this very fast and leave it to question time. The last thing I was going to talk about was just the idea of a chemical potential. You've noticed that quite apart from the strength of the signal in the most obvious sense, there is the fact that you get Boltzmann suppressed so quickly. When masses are above the Hubble scale, you rapidly get Boltzmann suppressed. So there's a narrow window. If you're too light, as Marcus's question revealed, when you're too light compared to the Hubble scale, it's hard to see you as a distinct particle propagating. If you're too heavy, you're Boltzmann suppressed. So the window is so narrow. Can we open the window? That's what this chemical potential thing allows. It's a special case of a derivative coupling where you couple a current made out of the heavy particles to just one derivative of the inflaton. Now, if you try to make a current out of a single scalar field, say sigma or chi or whatever we were calling it, there's no way, it's always 0. But if you have a pair, now if you have a pair of real scalars, you can form a non-trivial current, or if you have a complex field, you can form a non-trivial current and couple it in this way. And that turns out to be the magical thing, because first of all, just in terms of pseudoscience, you'd say, well, a non-derivative coupling of a current to this derivative of the inflaton. Now, the inflaton is mostly just its bev, its classical behavior, which is only time dependent. So that's that. And in slow roll, this time-dependent velocity is approximately constant. So this is like a constant, and it would multiply just the 0th term. If we think of what we have been studying up till now as being the sort of Boltzmann suppressed by the Hawking temperature particle production, that's what we've been studying, then this looks like a kind of chemical potential term, okay? And you think, well, chemical potential can change the balance. There can be large particle numbers even in the presence of this Boltzmann factor if the chemical potential overcomes it. And indeed, this idea had been there in the literature for spin half particles and spin 1 particles in more complicated ways. But we found that in the case of applying it to heavy scalar particles, it's incredibly simple and incredibly transparent. I wish I could have shown you, but the quick way to say it is you can do a field redefinition where you find that operators made out of the heavy particle get multiplied by phases made by the inflaton. And these phases, as the inflaton rolls, these phases, the rolling phase is giving a very rapid high frequency because phi dot is so big compared to Hubble that allows that background frequency to produce heavy particles. So I'll just say quickly that you can do the diagrams with this chemical potential effect. And there you can see that for masses even much bigger than Hubble, as a function of the squeezing parameter, the ratio of momenta, if you look at the non-Gaussianity, you see that you get very, for different choices of parameters I won't explain, you get very interesting oscillatory behavior, right? The kind of thing you can't miss. When you see these pictures, you are literally seeing, if that came out of the data, you would literally be seeing the propagation of the heavy particle, with its wave function. That's what you're seeing here. Okay, I better stop. Quick summary. Inflation gives us an incredible opportunity in principle for doing extreme particle physics in the form of these primordial correlators. What I've been studying, and I'm still studying actually in a variety of projects, is applying it to the most obvious targets, gauge-Higgs theory and extra dimensions, things like that. It's important to say I've been couching everything in terms of slow roll inflation. We don't really know the dynamics of inflation yet, not from experiment. And that greatly affects the strength of the signals, as you can see, even in the curvaton paradigm, which is only a modest departure from standard inflation. It makes a huge difference. So as we are sort of trying to understand what inflation could be, we're also trying to understand what you could see by virtue of it in cosmological correlators. For example, one of the things we're working on right now is a kind of warped extra dimensional curvaton. I guess if it's me, I'm supposed to work on warped things naturally, and so I'm doing that. And of course, one of the things you gain is you can see how one can gain, instead of say looking at the Kaluza Klein graviton with its Planck suppression, one could get something which is redshifted in the extra dimension to be, or warped in the extra dimension to be stronger, and then you get a stronger signal. Anyway, that's the spirit of it. I'll stop there. Thank you.
More questions? Raman, maybe you would have to look at, or can somebody look online to see if anybody on Zoom is raising their hand?
Nope. Don't hold that.
So could you say a little more about, if one saw this kind of a signal, what would you learn about the particle? One thing you said is its mass. Is it a kind of thing where you have to know the detailed model to know the signal, or is it like a resonance that you know, there's a sort of a
Yeah,
universal.
it's much more like, it is much more like a resonance. For example, yeah, that's a good way of thinking. What if I didn't know the theory and I was just showing, and I just saw this data, right? Or that data. Yeah, what you would read off from that is the mass. And if I had on another axis, if I showed you the angular dependence, where the angle I'm talking about is the angle between the hard momentum and the soft momentum in the squeezed limit, then that would give you the spin. So you would be, so it's a kind of spectroscopy. Now, at a more detailed level, but maybe it would be harder to extract in a model independent way, you'd be learning about couplings and so on. But that would be harder. So you see, it's very, it's limited. It's like you're doing spectroscopy, but the more you know in advance about what you might be hunting, the better it would be. Which is why I showed you the spin 2 case, because, you know, when you see spin 2, you are at least down to a smaller set of things that it could be, rather than just seeing some random scalar. The other case where knowing more might help you, but then the data would, is if you could really do something like, if you could really measure masses, like measure this mass and measure this mass, you would get this ratio, right? And if you were to guess, if you even guessed, hey, wait, maybe I'm seeing the standard model. Maybe I'm seeing a scalar, spin 1, another spin 1, but in a kind of pairwise production, and spin half. Maybe it's the standard model. Well, how would you test that? You would have to look at mass ratios in this way, and looking at, you know, here's the spin 1 divided by the spin half guy. And you would have to see, oh, wow, it looks like the couplings, the dimensionless couplings of the standard model, but run up to some scale at which inflation is taking place. That's to me, this is an incredibly exciting field theoretically, but it's it's incredibly difficult experimentally if you know nothing. Of course, it'd be really cool to just see something oscillating like that and say, oh, look, I see a spin 1 particle and it's got a mass of 10 to the 12 GeV. That would be really nice. But to give it a greater interpretation, it really does help to have some prejudice about ratios and spins and so on. The only theory of that sort that I know best is the standard model itself, like this thing here, or something one-off, like seeing a spin 2 particle, trying to, or maybe even if you're really able to, this is what I'd like to work on next. Can you use this chemical potential enhancement to see even like a KK tower of Kaluza Klein states, of KK gravitons, say, to see a tower of spin 2 particles, you would, you know, if you even saw 2 of them, you're starting to think this is an extra dimension opening up in front of me. I think we're limited to that kind of thing, sadly. I mean, I don't know, it's on the cusp of being super exciting and being very frustrating. I don't know how to come down yet. And I'm still going through the exercises of trying to generalize every trick known.
What about the energy scale of this collider, the Hubble? Is there a way of actually?
Yeah, that's the amazing thing, of course.
Yeah, go ahead.
Yeah, so as you probably know, the so-called scalar or tensor to scalar ratio R is something that is where you're taking the ratio of the scalar perturbations to the gravity wave perturbations seen in B modes in the polarized CMB. If we measure those B modes, primordial B modes, and extract a value of R, that directly is a measure of the Hubble scale during inflation, because the closer the Hubble scale is to the Planck scale, the bigger is the production of gravitational waves. So we know exactly how that works. And if we see it, if it's big, in other words, if inflation is high scale enough, then we are going to detect the scale of inflation, and we'll know.
But this,
My reading after playing with a lot of theories of inflation, if you ask me, is it going to be high scale inflation or low scale inflation? My own guess in terms of what is easiest to robustly get inflation is that high scale inflation is likely to be true. And so I am expecting that we are going to see a non-zero tensor to scalar ratio, and hence are going to know the scale of inflation. That's my guess.
I was wondering if you don't get any additional handle on that from these kinds of observables, like somehow the everything is sort of ratios of scales within this sort of observable.
Yeah. So you can indeed do that. I think if you take these, so just as an example, but maybe there's an easier way, but just from this set of guys, even if you didn't know what the scale of inflation was, but if you just took the mass ratios of all of these guys and you kept running up the mass ratios, remember the mass ratios are really dimensionless couplings of the standard model, and you just keep running them up. And at some point, those ratios look like what you're seeing in the sky, then you'd say, that's the scale of inflation.
Right.
These are in principle possible. I think all of them look like, gosh, you got to be kind of lucky that it all works out on your watch. But I don't want to say that you have to be lucky. My own attitude at the moment is the first exercises you do in this game, they're very exciting field theoretically, and they also look like they're tough, like you have to be lucky. But as time is going on, we are finding generalizations of the baseline mechanisms, and they require less luck because they're more robust. They operate in a broader space of parameters. I don't know where we're going to end up. It may be that they're more robust mechanisms, but you still need a good deal of luck going your way. Or maybe we're going to be led by generalizing and generalizing and generalizing to something that looks, we'll find ourselves in a different place where there's something very exciting and robust that we can do. I don't know as yet. I'll conservatively say it's going to be hard. It's going to require great luck and incredible, just to say what's the experimental side of it. It's going to require incredible experimental ability to pull off the kind of precision, like this. That's incredible precision by the standards of cosmological collider physics. You may require this high redshift 21 centimeter cosmology. To even do that technically, people are talking about instrumenting, putting the detectors on the far side of the moon to escape all the background from Earth. Those are really big reaches for budgets and scientists. And then theoretically, whatever non-Gaussianity you see, you have to remove all of the non-Gaussianity created after the Big Bang, after modes re-enter the horizon and start interacting gravitationally or however. There are non-Gaussianities there. You need to understand and subtract that. Now, we are in regimes where that can be done perturbatively in principle, but this is sort of a high order precision game for theorists. So the entire thing is why I call it extreme, because it's extremely demanding on every front possible. I remain hopeful.
Other questions?
How well can you measure the spin of the particle? How well you can measure the theta distribution?
Sorry, could you repeat that again, just a little slower, because I think I'm getting the sound is not great from your corner of the room.
Okay. How well can you measure the theta distribution?
The angular distribution.
Yeah, I think actually quite well. I think so actually, this is one of the great handles, that not only is there a background from contact interactions with this inflaton having with itself, or from very light particles, which effectively look like contact interactions, as I told Marcus. But all of those plausible things that are not propagation of heavy particles tend to be, again, in the sort of garden variety models, they tend to be theta independent, right? So actually seeing the angular sense, the angular distribution, like cos squared theta minus the third, my understanding is that actually should be a pretty clean thing to see. And it would also discriminate against a lot of the foregrounds of processing after the Big Bang and contact interactions during inflation. So I think it's actually a huge handle on extracting this signal.
Okay, thank you.
I see something in the chat here. Oh, great, just a comment. Okay. Gone to get a haircut.
Well, I think, so if there aren't any more questions, let's thank Raman, and we'll stick around unrecorded for further discussion. Thanks a lot.
Thank you.